In my previous videos, I programmed microcontroller AT89S52 using assembly, implementing different examples. In this video, a password identification system using the Atmel microcontroller programmed in assembly will be presented. A circuit diagram of the implemented system is shown here. As input peripherals, we have an 8-bit dip switch is interfaced to port P0, and we have a push button connected to port P27. We also have output peripherals interfaced with the microcontroller, such as an active buzzer connected to port P10, and two LEDs connected to ports P11 and P12. All of the ports of the microcontroller are held high by pull-up resistors. The reason for this is that this microcontroller can sink current well, but it cannot source current well. The circuit represents a simple password identification system, where the user, through the dip switches, inputs an 8-bit binary number representing the password, which is fed into the microcontroller, and then the user presses the enter button so that the input number is compared with the stored password. If the correct password has been entered, then the blue LED will be on for a second, indicating the correct password. Now, when the user enters an invalid password, the red LED will be on for a second and the buzzer will sound an alarm. The user will be given 3 attempts to input valid passwords. If on the third attempt an invalid password is input, then the 2 LEDs will start blinking. And now for a quick demonstration. First we enter the correct password. Now we enter an invalid password 3 times and see the effect. Let's have a quick look at the assembly code used in the project. We start by initializing 0 to register R3, which is used here as a counter to keep track of the number of invalid password entries. Next we set port 2 for input, and then we check the status of the push button connected to port 2.7. If it's not pressed, then this statement will be ignored and the program will go to this statement, which will jump to label loop 1, and we have a loop here that will continue looping until the button is pressed. When we press the button, this instruction will be executed and the program will jump to this label compare, where we will set port 0 for input, and at port 0 we have the 8-bit dip switches connected. Next we get the byte from port 0 and store it in the accumulator, and then we compare the content of the accumulator with the password 81 hexadecimal. If they are equal, then this statement will be ignored. So when the user enters the correct password, this instruction will be ignored, and the program will then turn on the blue LED and turn off the red LED. To keep the blue LED on for a few seconds, we call this function delay, which will be repeated 9 times through this loop here, where register B is used as the loop counter with initial value of 9. After the delay, the blue LED is turned off and the program jumps to loop 1, where it waits for the next password entry. Now, if the user enters an incorrect password, then this instruction will become true, and the program will jump to this label not equal, which is here. At label not equal, we increment the value at register R3, which is a counter used to keep track of the number of invalid entries, and then we turn on the buzzer and turn on the red LED, and then we apply some delay. After a second or two, we turn off the buzzer and the red LED, and then we check the value of R3 if it's equal to 3 or not. If not, then we jump to loop 1 and wait for the next password entry. If the byte in register R3 is equal to 3, it means that 3 invalid attempts were performed, and this instruction would be ignored, and the program will then blink the 2 LEDs on and off 10 times by using the counter in register B. Next, we reset the counter in R3 to 0 and then jump to label loop 1 and wait for the next password entry. Finally, subroutine delay, which is based on a 3-level nested loop, was explained in my previous video. A link to the assembly code will be provided in the video description. The final step is to generate the Hex Code from the assembly code by using the Keil IDE, and then we load the Hex Code onto the microcontroller. Please watch my previous video where all of this was demonstrated in detail. In a future video, I will interface with the microcontroller EEPROM AT89S52 to extend the flash memory capability of the controller. Thank you for watching.